Hi, welcome to lesson 15G, Derivatives of Trigonometric Functions. The goal of today's lesson is to differentiate trigonometric functions. First, a little background on what trigonometric functions are and how they came to be about. Well, maybe not the whole how they came about, but suppose we have a circle and we have some point on the circle that is 1 unit away from the origin, and we start spinning it around the origin. We rotate it about the origin. We'll form a circle here. So suppose the point stops along the way there, and we will connect what's called this terminal arm to the origin. We'll drop a perpendicular down to the horizontal axis or the x-axis, and this is our radius, and in this case our radius is going to equal 1, and here is our angle theta. In comparison to this angle theta, this side is our opposite side and this side is the adjacent side. Now the opposite side happens to also be parallel to the y-axis, so that's going to be our y direction, or y measurement, and the adjacent side is parallel to the x-axis. So this point up here is actually point P, which is x, y. Now, if we use our primary trigonometric ratios to look at this theta, we know that sine of theta is equal to the length of the opposite side, divided by the length of the hypotenuse. Well, in this case, the opposite side is y, and the hypotenuse is r, but in this case it's 1. So I'll put r there for now, but it's going to be equal to 1, and because r equals 1 unit, then that means that sine theta actually just equals y. If we then continue this and we look at the cosine of theta, we can see that we know that the cosine theta is adjacent over hypotenuse, and the adjacent here in this case is x, the hypotenuse is r. We know the hypotenuse, the radius, is 1 unit, therefore cosine theta is just actually equal to x. So our point xy here can then be summarized in terms of trigonometric ratios, and it can be seen as cosine theta sine theta. So if we know the angle theta through which this terminal arm is rotated about the origin, we can find the cosine and the sine of that angle, and that will give you the coordinates of this point. Also, to note, if we take the tangent of theta, well, tangent of theta here is opposite over adjacent, and we know that sine theta is actually y, so I can substitute this y for sine theta, and the x is what we just found, cosine theta, so tangent theta actually equals sine theta over cosine theta. Very handy. So if we were to rotate this about the origin, we can find the graphs of sine theta and cosine theta when we compare the position of this point P on the unit circle, compare it to the time of rotation. When 1 radian of revolution takes 1 second, then that means that the entire circle will take 2 pi seconds to rotate about the entire around the entire circle. So because the entire circle is 2 pi radians, and each radian is 1 second it takes to rotate, then therefore if it rotates 2 pi radians around, it's going to take 2 pi seconds to go around the entire circle. So the y is sine theta. We'll look at sine theta first. Sine theta is the y value, the vertical value of the of this point on the circle. We can look at like 4 main points here. This point, well, if the radius is 1, then that means that this point, in terms of x and y, is actually going to be 1 and 0. As the point rotates up to the top here, the radius is still, of course, 1. That means this length is 1. Therefore, this point is going to be 0, 1. If we continue rotating about here, that is, of course, still 1, but now it's on the negative side. So this is going to be negative 1, 0. And then it continues around here, and this is going to be 0, negative 1. And then when it comes back here, obviously it's going to be 1, 0. So this is 0 degrees rotation when it starts. It's going to rotate up 90 degrees, or pi by 2, to get up to here. It's going to continue rotating around to 180 degrees, or pi radians. So this is pi by 2 radians. This is pi radians of rotation. And then as it rotates around here, that's 270 degrees, which is 3 pi by 2 radians. And then it continues rotating around up to here, gets back to the beginning again, so it started at 0 radians, and then it ends off at 2 pi radians. Okay, so that's how all the rotations occur. So if we go through all these main points, 0 radians, pi by 2, pi, 3 pi by 2, and 2 pi, there are actually 1, 2, 3, 4, 5 main points, key significant points, that we'll look at going around the circle as we rotate this point P around the circle, which gives us, of course, here's one section, here's another section, here's another, and here's another. Of course, there's one section in every quadrant, there's 4 quadrants, therefore there are 4 main sections of these sine and cosine curves that we're going to take a look at now. So if I know that at 0 radians, the point here has coordinates is 1, 0, and I know that the points are actually, the coordinates are actually cosine theta and sine theta, that's what represents those 2 points, then at 0 radians, cosine theta equals 1, sine theta equals 0. So if I look down here, I'm going to break this circle up into those 5 main points. Here's 0, here's pi by 2 radians, here's pi radians, here's 3 pi by 2 radians, and here's 2 pi radians. So when the angle theta, angle of rotation, is 0, then sine theta actually equals 0. And this is the theta axis. So at 0 radians, sine theta equals 0, therefore for this sine graph, at 0 radians, sine theta equals 0. Then as we rotate up here, we get pi by 2 radians. Sine theta is actually equal to 1. So at pi by 2 radians, sine theta, the height of it is actually going to be 1 unit. Then as we continue rotating about here, we get down to pi radians of rotation. Sine theta is actually equal to 0. So therefore, pi radians, sine theta equals 0. We continue rotating this point P around about the origin. We get down to 3 pi by 2 radians, and sine theta is equal to negative 1. So at 3 pi by 2 radians, sine theta, the height of that is negative 1. And then we can see we continue rotating about to 2 pi radians. Sine theta is now back to 0 again. So we come back up here. Sine theta is equal to 2. So then we can draw a nice smooth curve through these. I'm not the greatest artist, but I'll try to make it as smooth as I can and hit all these points the best I can. So it's going to look very similar to that. So that's one wavelength, or one cycle, one period of the sine curve. If we had rotated this point P in the opposite direction, starting at 0 radians, we could go in the negative direction, negative pi by 2, negative pi, negative 3 pi by 2, and negative 2 pi. Then the graph would have gone in this direction over here. But this is the sort of the basic, the one cycle that we kind of look at, usually starting at 0 radians. And then of course this point can circle, like rotate around this about the origin many times or forever. Therefore this sine curve will continue forever in the positive direction and in the negative direction. Now if we proceed down to cosine curve, now is y equals cosine theta compared to the theta axis again. This of course is pi by 2, here's pi again, here's 3 pi by 2, actually I'm going to put this over here, 3 pi by 2, and 2 pi. So we can go through the same scenario again. At 0 radians, we see the point is 1, 0, and cosine is first, cosine theta is first, so that means that cosine is 1. So at 0 radians, cosine is actually at 1 unit away from the origin. If we rotate this point up to pi by 2, cosine is then 0. So at pi by 2, cosine is now down to 0. As we rotate around to pi, or 180 degrees, we see that cosine is now at -1. So we continue down here at pi, cosine is equal to -1. We rotate around to 3 pi by 2, cosine is back up at 0 again. So it comes back up to 0 here. And then when we continue that circle at 2 pi radians, cosine is back up to 1. Okay, so this comes back up to 1 here. And then we draw a nice smooth curve through these points, more or less like that. Okay, so this is the basic cosine curve, this is the basic sine curve, and these are the graphs that we'll be looking at as we look into the derivatives of sine and cosine, and of course tangent. So one thing I do want to do now is I want to take a look at some trigonometric software or geometric software to show you the vertical distance or the values of the derivatives as we look at sine and cosine. Okay, so I'll just switch over to that in 2 seconds. Okay, so here I've got some software, and this is the sine curve that's drawn here. This blue line is the tangent to the curve at point A, right here. This value of d is actually the value of the slope at that point, the slope of the tangent at that point. And we see up here we've got other values. This is the x value of this point A. Here's the y value of the point A. And this is the slope of the tangent. And it has, we also have this this little table up here too. So what I'm going to do is I'm going to start dragging this point A through along this curve, along the sine curve, and the tangent line is going to be going up and down as we go through this curve. But I want you to pay attention to the value of d, what this point D traces out as we go through the sine curve. So remember that this point D is the value of, or the gradient of the tangent line at point A, which is the gradient of this curve at any point along the curve. And so it is the derivative function, the gradient function, because it's the slope of the tangent, the gradient of the tangent, which is the gradient of this curve. Okay, so as I start dragging this, watch what happens to point D. So the tangent, of course, is changing as we go. Get here to 0 again. We've got another horizontal tangent. We see that D is back at 0. We continue dragging this point through the sine curve. Get back to another, well, almost horizontal tangent. D is back up to 0 again. We can see the slope of here, the gradient, is back to 0. And we continue dragging through this point through the sine curve. Notice what kind of curve is being traced out by the derivative. Look at this derivative function. The red graph here is the derivative function. What graph does that look like? I think I can actually... Can I press play on this? I think I might be able to. I don't know how to do that. Anyways, notice that the function, the derivative function, what kind of function is that? That actually is, so the derivative of sine curve is actually the cosine curve as we go through the cycles. And now here is the same sort of idea, but now we have the cosine curve. And here's the derivative, the gradient of the point A, the gradient of the tangent to point A, which is also then the gradient of the curve at that point. And if I trace out along point A, all the way along for this y equals cosine curve, what do you notice about the graph of the red function as we go here? What does that red function look like, which is the derivative function to the main function we're looking at, cosine theta? What does that red graph look like? It starts at 0 here, well, I mean, it goes through the origin, and then goes down to the minimum, up to the maximum, and then back down to 0 through one wavelength, which actually is the reflected sine curve, reflected in the x-axis. So this tells us that the derivative of the cosine curve is actually the vertically reflected sine curve. So that is our investigation for these functions. So what we just learned is that if f of x is sine x, that means that f prime of x is cosine x. Also, if f of x is cosine x, the derivative, or the gradient function f prime of x, is negative sine x. And another function, if we were to extend all these concepts, if f of x equals tangent of x, then f prime of x, the gradient function, is actually 1 over the cosine squared x. And along the way, if we just extend this a little bit further, if f of x is sine, or let's say g of x is sine f of x, then g prime of x is going to be cosine f of x multiplied by the derivative of f of x. So now again, using the chain rule, if g of x is the cosine of f of x, so we've got a function in as the angle, then the derivative function, the gradient function g prime of x, is negative sine f of x multiplied by f prime of x. So it's the derivative of the trigonometric part of the function, then we take the derivative of the angle, which is then f prime of x. And then the last one, if g of x is the tangent of f of x, then g prime of x is going to be f prime of x all over cosine squared f of x. So again, we take the derivative of the trigonometric function, the tangent part, it becomes 1 over cosine squared f of x. Then we take the derivative of the angle, which in this case is a function, f of x, and then we just multiply it with the original derivative, and so that we're multiplying by f prime of x. So we're going to see how all of this stuff works tomorrow in class. But in the meantime, please take a look at example 13 on page 380. And then after you do that, take a quick perusal of questions 1, A, B, C, E, G, H, I, 2, A, B, D, E, G, H, I, K, and 3, A, C, E, F, G, J, K, along with 4 on page 380. So there you have it for the derivatives of trigonometric functions. Thanks for watching, and we'll see you in class.